Hello, this is the next video in a playlist that I'm calling Probability Measure, and here we're going to look at the theorem of total probability. So the theorem says let B1, B2 form a finite or countably infinite family of mutually exclusive and exhaustive events. That is, that BI are disjoint and the union makes up the entire space, omega. So omega is equal to this infinite union of BI. Now, if A is any event, then the probability of A can be represented like this. It's the probability of A intersect BI summed over all I. Now, hence, PA is calculated by making mutually exclusive and exhaustive ways in which A can happen, and then adding the individual probabilities. Now, B in this theorem says probability A is equal to the sum of this, probability of A times probability A given B, where the sum is taken over all I for which the probability of BI is greater than 0. Now, hence, PA is a weighted average of the conditional probabilities of P, the probability of A given BI. And let's prove those. They're short little proofs. So the probability of A is equal to the probability of A intersect omega, right? That is just A. But omega can be written as the infinite union of BI's. So the probability A intersect BI is this. But the intersection can be distributed over union. So this inside is equal to this. So it's the probability of the union of A intersect BI. But each of these sets are disjoint, and the probability that is equal to their sum. So it's the sum of the probability of A intersect BI. Well, that's what we wanted to show. Now, for B, A intersect BI is a subset of BI, the event BI. So that means the probability of this intersection is less than or equal to the probability of this event, BI. So thus, if its intersection is 0, if the probability of BI is 0, right? If this is 0, that has to be 0. Now, since we know that the probability of this intersection is equal to the probability of BI times the probability A given B, often you see this piece divided down here, and that's the conditional probability. But if it's multiplied up, then this relationship still holds. But given this, then the result follows, right? That it is true. And the theorem's proven. Let's do one example and then call her quits for this video. Let's let I equal n, where n goes from 1 to infinity, with the probability that I is equal to n is 1/2 raised to the nth. Now, if n is observed, whatever number that is, a coin is tossed with probability e to the minus n of a head. And we want to find the probability of tossing a head, or flipping the coin and landing head. So the answer is this. So let A be the event that the coin lands heads, and Bn, of course, is the event I equals n. And what we stated up here, the probability of A given Bn, so that means that we know the number that I takes. So the probability of A of a head is e to the minus n. But that's not what we want to know. We want to know the unconditional probability of observing a head, the coin lands heads. So this is equal to, using the total probability, that the probability A is equal to this infinite sum, where we introduce this variable but sum it over all possible values. And this can be written in the conditional form. But we know each of these, the probability of I is equal to n is 1/2 to the n. Probability of A given Bn is e to the minus n. Well, these can be rewritten in this form. But 1/2 to the e is less than 1, and it's positive, so we can use the geometric series to calculate this. So this is equal to whatever the first term is, right? When n is 1, then we get this term, and then it's 1 minus this term, which is here. And this can be simplified to this. So 1 over 2 to the e minus 1 is the probability of tossing a head. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.